And the first keynote we have is Gerhard Krinner from the IPCC, and he's basically setting the scene. So just a very quick introduction. Gerhard is a modeler of climate, and his particular field is polar ice cap modeling and how they influence the world and the climate in particular. You've probably all heard about tipping points in the climate debate. So this is basically his realm, let's say, and it took him all over the world. So he's been working in Melbourne and faraway places like the Antarctic and Potsdam. So he's going to talk about the sixth synthesis report, of which he was coordinating one of the parts. And he's going to give us some key messages from that report. So please welcome to the stage, Gerhard Krinner.
Figure out. So thank you for INCOSE for inviting me to give this keynote talk. I'm really honored to do this. So as you see, I'm going to deliver a few key messages of this sixth IPCC synthesis report on climate change. Now let's figure out whether this works. It does. First thing I'm going to show you is that, that climate change thing has been known for a very long time. Person you see here is Syukuro Manabe, who got the Physics Nobel Prize in 2021, 1 year ago, for the physical modeling of Earth's climate, quantifying variability and reliably predicting global warming. And that was work done in the 1960s. And what he did was a one-dimensional model of the atmosphere, taking into account the greenhouse effect. And what you see here on the right is a graph from his paper from the 60s. On the horizontal axis, you see temperature going from -80 to +30. I hope you can read that. And the vertical axis is just cut through the atmosphere, so that's the altitude. And as you know all, temperature decreases in the troposphere when you go up. So the pilot tells you, you know that well, 10 kilometers altitude. So we are flying at 10 kilometers altitude, it's -50 outside. That's what you see here. And then you get a stratosphere where temperatures get warmer again. Okay, so that's the black curve, if you want, normal atmosphere. And what he calculated was the temperature profile in the atmosphere when CO2 concentrations double. That's the red curve. And you see it gets warmer in the lower troposphere, but it gets cooler in the stratosphere due to the greenhouse gas effect. So that's a unique fingerprint of the greenhouse effect. Warming in the troposphere, cooling in the stratosphere. If, for example, climate change was due to a modified solar activity, you wouldn't have that unique fingerprint. You would have warming throughout the atmosphere. So that was predicted in the 60s, and that is what we observe today, right? We observe a cooling in the stratosphere. So he got his Nobel Prize for that. And there's another part of the Nobel Prize for Klaus Hasselmann, a German, who has been working on statistical methods to answer the question, when you observe climate change, what is it due to? So that's what we call attribution. As attribution, it's always shown with these curves you see here. We use climate models, force them to, or ask them to calculate climate evolution in the absence of human activity without increased greenhouse gases. And we get this blue curve. And when you calculate climate evolution in the climate models, taking into account the greenhouse effect, you get these red curve. And the black curve is the observed one. So that's how we simply show the effect of the climate change, of human forcing. The real attribution methods are much more complicated, actually. Anyway, I'm going to talk about that afterwards. Good. So short message. Climate change and prediction of climate change, that's an old story. We've been knowing that for a very long time. And it's really sound, firm physics, because you don't get a Nobel Prize, a physics Nobel Prize for something that isn't really sure, right? If you get a Nobel Prize for something, that thing is made in concrete. Okay, so I'm going to deliver you a few of the key messages of the IPCC synthesis report. So a few words on what the IPCC actually is. That's the Intergovernmental Panel on Climate Change. It's about 1,000 scientists that have been asked by basically the United Nations to provide an assessment of the state of the science. What is that made for? That is made for to serve as a scientific basis, a recognized scientific basis for the international negotiations on climate change. When you got these annual COPs, you know, COP 21, 27, 28, and so on, politicians come together, talk about what can we do about climate change. They talk about what they can do. They will not talk about climate change itself, because that is a recognized, that they have the recognized scientific basis that has been written by the scientists. So they won't discuss, is climate change due to humans? That is made by the scientists. Okay, so we have, over the last assessment cycle, which took like 8 years, written a few reports, special reports, like one on global warming of 1.5, ocean and cryosphere, and so on. So these are the 3 reports on the left. And then we have 3 working group reports, which are really like 1,500 pages each on physical basis of climate change. That's my home. I'm a physicist. One on impacts and vulnerability, and one on climate change mitigation. So these reports were published in 21-22. And then a small group of us, like 30 people, wrote this synthesis report, which is quite short, like 50 pages, and which synthesizes, as the name says, the entire number of reports that was published before. So altogether, 1,000 scientists. The reports are entirely based on published scientific literature. 85,000 articles have been cited in these reports. Now, if you take a normal scientific paper, like 10, 15 pages, multiply it by 85,000, that's 1 million pages of scientific literature. That gets compressed or condensed in the synthesis report in 50 pages, which has a summary for policymakers, which is 20 pages. So we have condensed like 1 million pages of scientific literature into 20 pages in the end. There's a public review of these, so we get 300,000 review comments overall from governments, from experts, taken into account and so on. So that's these IPCC reports. Okay, so the synthesis report was approved in March 2023, so a few weeks basically ago. I'm going to talk now about where are we today with climate change. So first thing, as you probably know, cost of renewables, source of energy, decreases strongly. So market cost decreases, the market adoption increases. For example, photovoltaics, onshore wind, offshore wind. And the yellow line here you see is the fossil fuel cost. So actually photovoltaics is, not more expensive anymore than fossil fuel. Same for onshore wind. So that's good news. But still, greenhouse gas emissions continue to grow. So these are the emissions. You have CO2 from fossil fuels, that's the lower one, CO2 from land use, cutting forests, for example, and then the known CO2 emissions like methane and so on. They continue to grow. The growth is, slowing down, but still this year, we're gonna set a new record probably of greenhouse gas emissions. And they're not equally distributed. So on the left side, you see the emissions, cumulative emissions per region since 1850. So of course, North America and Europe, historically, the developed regions have emitted most, no surprise at all, Eastern Asia and so on. On the right side, you see horizontal axis, the population, vertical axis, the greenhouse gas emissions in 2019. Still North America emitting the most, but Eastern Asia, for example, now emitting a lot, and there are a lot of people. So that's the vertical axis is per capita, right? So the integral gives you the total emissions. That's why you see that China is now the biggest emitter, actually. Europe is an interesting point. You see there is something below the horizontal axis. That's the reddish or slightly pinkish part of it. That's because forests are regrowing in Europe, drawing down carbon. Because we have cut all the forests like in the 1800s or even before, now we're regrowing forests, so that gives us a negative emission in Europe. Okay, so emissions are diverse by historical responsibility, diverse by regions today, and of course, within each country, you have a strong inequality of emissions. Like 10% of the households with the highest carbon footprints in the world cause 40% of the global emissions, and 50% of the households with the lowest carbon footprint, only 14%. So you have the diversity between the regions, between the countries, but also within each country. So the greenhouse gas concentrations increase with the continuing emissions, of course. So we're setting each year new records. These are numbers from 2019. Today we are at 420 ppm of CO2, and the same for methane and nitrous oxide. Now, of course, climate continues to change with that. You see the observed temperature over the period which we really look at, like from 1850 to 2020 to today. We take as reference usually 1850 to 1900, and you see it has been relatively stable and increased at the beginning of the century, decreased a little bit after World War II, and then increased since the 70s, basically linearly and continuing to do so. Now, with these attribution methods, we're able to say how much is due to what. So we have the observed warming on the right side, which is today 1.1 degrees compared to the reference period, which is 1850 to 1900. And the total human influence is basically the same. So that's the second red bar on that graph. It's also 1.1 degrees. So human activity has caused basically the entire change we observe. But it's a bit more complicated if you look into details. Well-mixed greenhouse gases are, so CO2 and methane, have caused 1.5 degrees of warming. And there's cooling effect by aerosols, which basically shade the sunlight, shade the Earth from the sunlight and cool the Earth. So that's 0.4 degrees of cooling. There's also an assessment of what solar variability has caused. So solar forcing is actually negative since the 1980s, which means that solar activity has decreased. So in no way solar activity can explain a warming, right? So that's basically zero. And internal variability is also over that long period, zero. Good. If you look into more detail, that's the graph on the right side. You have a lot of different effects. So you see aviation contrails, for example, have a slight warming effect and so on. So we have done all that work, but the big ones are well-mixed greenhouse gases, notably CO2 and methane, and the sulfur dioxide, which causes these aerosols that shade the sunlight. So yesterday evening, I was told that I had a little bit more time, so added a few slides, but I think I won't go into that much detail. So there will be a few slides that I will be shunting right now, so don't be surprised. So this is the curve you've been seeing already. Again, the black is the observed, the red one is now the greenhouse gases, and the blue one is the aerosols. And if you look in detail, you see that the greenhouse gases really have taken off like in the 70s. That's when we really started emitting like hell, right? The aerosols have been cooling quite a long time, and this is what explains this cooling period after World War II to the 1970s. That's actually a compensation between the greenhouse gases and the aerosols. And it's well understood. Anyway, so these have different fingerprints. Greenhouse gases on the top left, there's warming in the Arctic, warming over the continents. The aerosols have, because they have been emitted on North America and Europe, especially, a very different fingerprint, a localized fingerprint, cooling over North America and Europe, right? And you have the same for precipitation. They also have different fingerprints. That is basically what allows you to do the attribution, the spatio-temporal fingerprint of these different forcings. Anyway, I'm going to skip through the next slides because I think that's going to be too long. I had a few aviation slides. If you have questions on that specifically, I can give you some answers there. Now, History of IPCC attribution statements. IPCC made its first report in 1990. 1990, climate change was like 0.6 degrees. Compared to today, it's 1.1. So it was weaker because we have this linear warming trend. So in the first IPCC assessment report, statement was the size of this warming is broadly consistent with predictions of climate models, but is also the same magnitude as natural climate variability. Now we are 30 years later, AR6 on the bottom of the page. Climate change has continued, science has improved. Now the attribution statement we have now is, it is unequivocal that human influence has warmed the atmosphere, ocean, land, widespread and rapid changes in the atmosphere, ocean, cryosphere, and biosphere have occurred. So, of course, now we know for sure what was something we kind of expected in the 1990s, because climate change has continued and science has improved. So, the global warming due to human activities leads to more frequent, more intense extreme events. So you see the regions here of the Earth. When it's in color, it means that an increase in warming, hot extremes has been observed, and it has been attributed to human activity. So that's basically the case all over the world. Same for heavy precipitation, but it's not attributed everywhere. It's observed in many places. That's the gray color, but it's not yet attributed because the signal isn't strong enough yet, but in many regions it is already attributed to human activity. And also for drought. Here, for example, in the Mediterranean region, of course, an increase of droughts. Okay. So we have generalized adverse impacts, losses and damages attributed to climate change. For example, for different sectors of human life, if you want. Concerning, for example, water availability. Water is a big problem, climate change. About half of human population on the Earth has already water shortages for some part of the year due to human and non-human factors. So that's on the upper left, the physical water availability graph. So we have both human and natural factors here. Agriculture, for example, we have adverse impacts from climate change. Now, agricultural yields over the last 50 years have been improving, right? That has been improved because the techniques, the chemistry has improved, fertilizers and so on. But the climate change itself has actually reduced the agricultural yields. So we have an adverse impact from climate change on agriculture and so on. What are the possible futures? Next part of my talk. Now, the clear message is that the future warming is going to be due to future emissions. What you see here, for me as a physicist, I have no crystal ball. I cannot know what the future emissions of greenhouse gases are going to be. Therefore, to do what we call climate projections, we have to make scenarios of future climate change, scenarios of future emissions. Now, the scenarios, you see them on the upper right here. So you have a time axis, horizontal, and a vertical axis. That's the emissions in billions of tons of carbon dioxide per year. Now, we make different scenarios. One scenario, like we decrease carbon emissions, CO2 emissions, and other greenhouse gas emissions very strongly. That's the blue one, or the light blue one. And then one, which is the yellow one, which says like, we're going to stabilize our emissions. And the red one, which is like, we're going to emit like crazy, right? As a physicist, I have to make these assumptions. I cannot know what is going to happen over the next 100 years. Now, the lower graph shows you on the same time axis, global mean temperature. So from 1950 to 2050, that's the observed. That's what we also calculate with our climate models. And then the colored curves on the right are corresponding to these emission scenarios. So there's one scenario that shows you that in which we would limit, because of the emissions reductions, climate change to 1.5 degrees. Today we are at 1.1. And there's others that increase and go on up to 4.5, 5 degrees. Now, if you look at the emission graphs here, you see that this light blue curve reaches 0 net zero CO2 emissions in 2050. Just look at that one. And the dark blue one is in net zero in 2070. So we emit as much as we draw down through innovative technologies, right? Or growing forests. Now, if you look, you see that at the moment of net zero CO2 emissions, the global mean temperature actually reaches its maximum, right? In both scenarios. So the timing of the net zero CO2 emissions is the timing of temperature maximum. It's the timing of stabilization. It's not the time when you come back to the climate before we started emitting. That's really an important message. Net zero equals stabilizing the climate at the level you have reached at that point. And that means that future emissions lead to additional future warming, because if we stop emissions now, climate is actually going to stabilize immediately, right, for the next 50 years or so. We won't stop emissions tomorrow, but if we did, climate would stabilize quite quickly, almost immediately. That's the effect of that's the combined effect of two different effects. I can explain if there are questions. It's a bit complicated. Now that finding leads to what we call the carbon budgets. Every ton of CO2 adds to global warming, to additional warming. So you see here on this graph, temperature on the vertical axis, so temperature change since 1850 to 1900, and on the horizontal axis, the total CO2 emitted since the beginning, since 1850. Again, black part here is the observed, so temperature has been increasing, and the horizontal axis in this is an implicit time axis, right? Because the cumulative emissions increase. We continue emitting, so we have an implicit time axis here on the vertical, on the horizontal. And then you have the colors for the different scenarios, and it's basically a linear relationship. So that's kind of frustrating for me as a physicist. We use these extremely complex climate models that take into account a lot of processes, use the most powerful computers of the earth, and at the end what we get is this linear relationship, right? That's fantastic. It has uncertainties, of course, as you see, but basically what it tells you is like, okay, you want to limit climate change to 2 degrees, go from the horizontal, from the vertical axis, go to the graph, go down, and you see how much carbon we can emit as humanity all together. And that's what we call the remaining carbon budget. We know how much we have emitted today. It's about 2,400 gigatons of carbon. And if you want to limit to 1.5 degrees, we have 500 left. Question is, and a political one, who gets to use the carbon, right? Who gets to emit the rest? That's not a physicist. That's not me to reply to that. Now you can compare these carbon budgets to, for example, how much we emit every year. That's the third bar on the left. If we have the 2019 emissions for 10 years, that's the bar here, then we basically arrive at 1.5 degrees. And we completely use up the carbon budget that we have for 1.5 degrees. Again, we are already at 1.1, so there's not much left. Today, we have fossil fuel infrastructures like coal power plants and so on. If you use them for the whole lifetime, we basically rush through the 1.5 degrees and almost completely exhausted 2 degrees carbon budget already. So building any new infrastructures basically commits us to going over 2 degrees. Now, 2 degrees is a political target. It's not the scientists who say, we should limit ourselves to 2 degrees. That's a political target set by the Paris Agreement. Okay. Now, I think you have understood humanity is not on a trajectory towards 1.5 or 2 degrees warming by 2100. You see here the vertical, the emissions, and the time axis. The red curve is the projected emissions from implemented policies. Well, politicians, have implemented policies to reduce CO2 emissions that basically would lead to a stabilization of emissions at the current level. And that will lead us to about 3 degrees of global warming. If we wanted to limit global warming to 1.5 degrees, we would have to follow, in terms of emissions, the blue curve, which means like 43% decrease of CO2 and greenhouse gas emissions by 2030. So that's huge. Okay, so current track is 3 degrees warming in 2100. Now, this climate change has, of course, a strong intergenerational aspect. Maybe you have seen this one. It's the same, it's a temperature, global mean temperature as a function of time, but in colors, has been increasing until 2020. And of course, and as a function of these scenarios, the future generations are going to be impacted differently, depending also on when they were born. So small child born today, we have it in our hands what temperature it will live. Now, I've shown you a global series. Let's go into a bit of regional detail. Regional changes increase with global warming. So you have here on the vertical axis, global mean temperature change, and on the horizontal axis, different variables. So we have an increasing frequency and intensity of certain types of extreme events, heat waves, droughts, and heavy precipitation, and of compound events with global warming. So it's always the same patterns, but they get more intense when climate changes, right? So we can look at more detail here. Hottest day temperature change, very strong in the mid latitudes and on the lower latitudes, also in the Arctic, basically over the continents, of course. Drought, measure of drought is the annual mean total column moisture change. So you see, for example, in the Mediterranean, it's drying. That's a very short signal, basically, we have. And of course, the stronger the climate warming is, the global warming is, the stronger these signals get. And precipitation, annual wettest day precipitation change, so a measure of the extreme precipitations that basically increases over all the continents. And to what degree depends on the global warming, of course. Now, these were examples of things that change basically in line with the global mean temperature. There's also effects that take much longer time, and the most important one is the sea level, because an ice sheet and the ocean, to warm up the ocean, that takes time. So that reacts slowly. At the current level of temperature, if we stabilize it, Greenland and Antarctica will continue to lose mass, and Greenland and Antarctica will then contribute to sea level rise over a very, very long time. It takes time to melt these ice sheets. But what is really important to recognize, even if we have this commitment, this millennial scale commitment of sea level rise, even over this century, we can reduce the rate of sea level rise by reducing temperature. So we can't reduce the fact that, for example, at 2 degrees warming, over 2,000 years, sea level will rise between 2 and 6 meters. We can't stop that, but we can stop how quickly you come to that over the next century. So for every additional increment of warming, health risks increase, same kind of figures you've seen before. I'm going to go quickly to that. Food production, same kind of effects get more pronounced. And species losses, of course, also, which increase with the global mean change. So adaptation and development influence the risks. Now I'm getting more into parts which I'm not specialist on, so please bear with me. My colleagues working on impacts visualize impacts and risks of climate change with these burning embers, as they call it. Vertical axis is global mean temperature change, and the color is how strong the risk, the assessed risk is. Now, you see on the left 3 bars for heat-related morbidity and mortality. And the 3 bars are for basically how strong are the risks, but in terms of, they depend on how good the adaptation is. Left one is we don't adapt to climate change, so failure to proactively adapt, low investment in health system, for example. And on the right, you have the small one where we do this very strong adaptation to health risk by investing, for example, in our health systems. So of course, the risk then increases much slower. Same is also true for food insecurity in different pathways. So that's the 2 right bars. If we are in a world where we have high challenges to adaptation, like high income, low income, no land use regulation, and so on, then we have high risks at the same temperature level. If we are in a world where there's high income, where there's low population growth, reduced inequalities, food produced in low greenhouse gas emission systems, effective land use regulation, high adaptive capacity, which is the right bar, then the risks, of course, linked to food insecurity increase less quickly. So in terms of adaptation, we see progress in planification and implementation of adaptation, but the responses are fragmentary. There are limits to adaptation. You can't adapt to any climate change, and a growing gap with respect to what is needed. And there's also maladaptation. So I won't define that here. If there are questions, I can do that afterwards. In terms of vulnerability and risks, what is really important to recognize is that the most vulnerable people are those who contributed to least to the climate change. Horizontal axis is 2019 emissions per capita, which are basically also linked to what people in different regions have emitted in the past. And the vertical axis is the vulnerability index. Don't ask me exactly how it is defined, but anyway, what you see is that people who emit less greenhouse gases, poor people, to put it simply, are those who are most vulnerable because they don't have the means to adapt, of course, to protect themselves. That's actually very obvious, and you see that on that graph. So we in developed countries, we have that ethical responsibility. We won't die from climate change, definitely not. Our kids won't. But those who are impacted are those who didn't cause it, and that's really our ethical problem. Now, as I've said already, planning for adaptation and implementing adaptation measurements takes time. I've shown the graph on the right side already. You see the lower part of that graph magnified on the left. This is how long it takes, for example, to build dams. It takes time to build a dam. It takes a lot of time in democratic societies to relocate people. If you know that an area is going to be inundated, it takes time to convince people to leave and build houses somewhere else, right? So this is what you see on the left, timescales of planning and implementing adaptation measures. And that's what I said before. If we slow down the rate of sea level rise, we get this time. It buys us that time we need to adapt to climate change. Now, last part of my talk, how can we accelerate action? So, as we said, we have to go quickly. If we want to limit the warming to 1.5 degrees, we have to act immediately. So this is an assessment of adaptation and mitigation measures until 2030. What is the potential and what is the cost? Now, the cost is given in color. Blue means it is actually less expensive than the reference. For example, for the energy, it's like reference would be burning fuel or gas. Blue means that the measure you're implementing would be cheaper than the reference. And the size of the bar means how much you can reduce emissions. So it's the horizontal axis is in gigatons of carbon equivalent, CO2 equivalent per year. So there's potential to reduce emissions by almost 3 gigatons of carbon per year from solar, from wind. These are the big ones, even at lower cost than the reference. Of course, when you go to the limits of that implementation, it gets more expensive. An important part of reducing emissions is the reduced conversion of natural ecosystems. So that's the second group here, the big bar, which is already yellow at the beginning. So that costs money, but it has a high potential. Carbon sequestration in agriculture, that's also important. Ecosystem restoration, afforestation, reforestation, there's a huge potential in that, but it costs money. Other opportunities. You see a lot of blue bars here on the upper part. That's efficiency, basically energy efficiency, switching also to electric vehicles, efficient lighting, public transport and biking and so on. That's linked to what we would call sufficiency, right? Switching to low carbon systems. So that's also a large part of individual decisions. The problem with climate change is that it concerns every part of our life, and it concerns every single person, every single decision we take every day, and it concerns all scales up to countries, political decisions on the international level. So every system, every scale, every person is involved. So we have also these individual decisions here. And another important part is also linked to food. Where was that? I think that was on the previous one. Shift to sustainable, healthy diets. That's a gray bar in the middle. Basically, that's a wording for eat less beef. Now, let me open a parenthesis. These IPCC reports are approved in a meeting between the scientists and the representatives, delegates of the countries, because the countries are bound by them. They recognize the science. Now, for them, in order to recognize the science, we have at the very end, we write a summary for policymakers, which is very short. Scientists write it. It's like 10, 20 pages. And then we have a week-long meeting where the scientists, together with the delegates of the different countries, discuss each sentence, and each sentence is approved. Now, you can well imagine that Saudi Arabia does not like what we write, right? For obvious reasons. Now, was there a question? Right. And it's your right, right? It's your country's right to not be happy with what we write, right? But they recognize it. So when we have that discussion now, sometimes it takes a week. It takes a week. These are very difficult discussions. Country delegates discuss with each other what the formulation should be. The scientists are there to say, this is backed up by the science. So there's nothing in the report that is not sound science, backed up by the scientific literature. But in order to get an agreement by each and every country, including, in this case, Argentina and Brazil, you sometimes have to find creative formulations. Now, the initial formulation in that report was plant-based food, right? Now, Argentina and Brazil, for obvious reasons, didn't want that. They wanted to, you know, do something that wasn't as clear. So the formulation that was found after hours of negotiation was like sustainable healthy diets, which basically to everyone means what was initially the formulation we wanted to write, but it is like a little bit softer to get the approval of every country. So the thing is, in the end, what is written in the IPCC report is sometimes like a little bit hidden, if you want, or there's formulations that are maybe not as clear as we would have written, but everything is there and everything is backed up by the science. Okay, I think this is the last one. Strong and rapid action is possible, including demand-side mitigation. That's what we call the efficiency. If you look for food, for example, current emission is huge. Like total emission today is about 60 gigatons of carbon. So total emission is like 20 almost. So it's enormous in terms of gigatons of carbon equivalent, but that takes into account the methane, gigatons of CO2 equivalent, excuse me. Now, by changing our diets away from meat-based to more plant-based, reducing food waste, reducing conversion of land to pastures and so on, we could be able, at the current level, to reduce the emissions linked to food by 44%. Same is true for land transport, switching to electric vehicles, which are then now powered by renewables, of course. Buildings, that's an isolation, and so you can also reduce the emissions very, very strongly. Electricity is particular, more efficient systems. I won't, oh, you are the specialists about all these things. It's your work. more efficient systems, reduce waste and so on. That could reduce the consumption very strongly. Of course, we would have to electrify massively by going away from fossil fuels, right? So that would increase the demand in electricity, but by increasing the efficiency, we would, by 2030 at least, in this very strong mitigation scenario, not increase the total demand on electricity. So again, it concerns everyone. It concerns individual decisions at city levels, regional levels, country levels, and international levels. And public policies and infrastructure really have a key role to make the low carbon lifestyles possible. You can't tell people to take public transports if there is no public transport, obviously, right? So that's the easy way to say it. Okay. The pace of the transition to net zero CO2 depends on the sector. This is a graph that shows, as a function of time until 2050, the emissions for different sectors, percentage reductions on the vertical of CO2 emissions with respect to 2015 for the different sectors. So you have one sector, which is the green one, land use change, where it would be possible to reduce the emissions, basically by reduced conversion of land, of forest to agricultural land, right? And by reducing methane emissions by cars, etc. That is, there's a strong potential for reducing quickly. It's much more difficult in energy supply and much more difficult in other sectors like the transport, industry, and buildings. Of course, you making a plane fly on batteries, that's a huge challenge, right? So obviously, these are hard to abate emissions that are taken into account here. So it depends on the sector, how quickly you can go to net zero CO2. And I think that is definitely the last one. Key condition, of course, is finance, technology, and international cooperation. Giving the countries, the less developed countries, the technical means to allow them to leapfrog from today's technological state to future is really important, but it's also a question of finance, of course. And what you see, for example, is the need you would have for different sectors to increase financing. For example, in agriculture, now that's the fourth line, I'm not sure you can read it, but the blue bars on the left is how much money is flowing into it in terms of adaptation and mitigation measures. And the gray bars are what it would be needed to achieve that reduction of greenhouse gas emissions. Now, for example, in agriculture, forestry, and other land use, we would have to scale up by a factor between 10 and 30 what is actually needed compared to the present day finance flows. So it's also, they also have a breakdown by region, by type of economy, but also by sectors. Basically in every sector, in every region, and by any type of economy, we would have to scale up the financial efforts to reduce the climate change. Again, please don't ask me too many questions about that kind of slides. I'm a physicist. Right, that's the last one. I'm proud because I put the SDGs here. You see them? Okay. That's the co-benefits between climate change and the other sustainable development goals. So climate change or climate action is sustainable development goal number 13. And what you see here on the right is the co-benefits or the trade-offs between climate action, so reducing CO2 emissions and adapting to climate change, and the other sustainable development goals. And blue means there are synergies, like, for example, one sustainable development goal would be clean air or safe, clean environment. Of course, you reduce the number of cars in cities, which is reducing CO2 emissions that go with it. That increases the air quality, right? Or replacing coal power plants by clean power plants, that increases the air quality. So you have these kind of benefits, co-benefits. So basically you're blue in most of them. There are also a few trade-offs. For example, if you say, okay, I want to plant a massive amount of forests because they draw down CO2, and then you convert agricultural land to forest, of course, that has a trade-off if people then starve, right? Because they have nothing to plant their seeds anymore. So you can't just say, we just have to plant trees everywhere, draw down a massive amount of CO2 and everything is solved. No, because you have that trade-off with the fight against hunger, of course. So there's one you see here that's on the second line on the right. That's the reddish, yellowish part you see here. And the effects, of course, depend on the scale of implementation. So sometimes you have benefits at the beginning, but if you go too far, then you go to trade-offs and you start getting trade-offs. Okay. Final message, our choices today will have effects for centuries and millennia, specifically the sea level rise. And that's it. Thank you.
Okay, thanks a lot, Gerhard. I'm thrilled to hear a modeler talk about all these things. And obviously, as systems engineers, we're used to dealing with complexity. And when you see the trade-offs and how it all connects in the end, we're clearly in a position to help, and we should really take that responsibility. So I'm fascinated by your talk, actually. Thanks a lot, Gerhard. We now have 10, 15 minutes for questions. And I see the first questions. I'm going to come to you.
Gerhard, thank you very much. It's outstanding and just what we needed. I wish we'd continued that discussion at the departure lounge at Charles de Gaulle yesterday, because we got close to the real issue I wanted to talk about. And that is, I think you've just shown what could be done by physics modeling, and I'm a physicist and I respect what you've done. I really admire it. My worry is the systemic factors amongst the mitigation factors. I'll just say two more words about that. What we're asking for is cooperation on a scale not seen. And because of past actions, we've released CO2 into the atmosphere at a point where things are happening that can't be stopped. We in our country are not exemplary in accepting migrants. Let's just put it politely. We treat them like an invasion force. We lock them up in old military sites as if they're criminals. And yet we're asking for collaboration from the rich countries to deal with the effects that we've vested on the poor countries. It's leading to nationalistic policies, people drawing up the drawbridge. The conditions for international collaboration now are less than they've been in decades. I think a systems approach ought to apply itself to how those things interact, not just the physics, which again is a brilliant piece of work, on the effects of them. And I think that's the opportunity for systems people. And I think I saw that we'd had this conversation too some years ago with the work of Donella Meadows and other people looking at limits to growth. I think there needs to be a systems model that brings in sociological factors and all sorts of other things as well. I know it's a very, very big question and it's beyond the scope. But the systems people have got to rise to that too. I'll leave it there.
Definitely. So in one of the graphs I've shown, we also talk about systems. Now, I don't talk about the transport system and so on. Don't know whether that applies to what you would define as systems, but you're perfectly right. Now, these numbers, for example, on climate refugees, or I don't know how you call that in English, these are very uncertain numbers. But what is absolutely obvious is that reducing the pressure, reducing climate change will, in the end, reduce the need for people to migrate. The regions that are going to become inhabitable in some parts of the year are the ones typically where people, where it's warmest, in tropical regions, so where the development is least. So reducing that climate change will, of course, be efficient in the long term to limit these demographic pressures and costs for us also. That's obvious.
Thank you for the talk. Very interesting. I have a quick question on the estimation of CO2 emission or the greenhouse emission. do we estimate it, or do we have an actual way of measuring things? How do we do that?
We know very well how much fossil fuel is used. The numbers are pretty clear. I mean, we know how much is used for fossil fuels. It's much more complicated for the other part of CO2 emissions, which is land use change. You need to rely much more on satellites and much more on estimates, much more on local measurements of how much does a replanted forest actually draw down in terms of CO2. So the uncertainties on that part are huge, but the uncertainties in terms of CO2 emissions from fossil fuel are really quite good. It's a few % of uncertainty based on that, because we have the inventories. We know how much fuel different countries buy and how much they dig up, and that's quite obvious.
Okay, we have online questions. How can you calculate and present independently costs of factors that are tightly related? I think that goes back probably to the first question we had. Sorry? Oh, the wrong field.
Yeah. As I said, I'm a physicist, so I do not know in detail how these calculations are done. Sorry. So this is my joker. I'm really sorry. I can't go into details how economists in working group 3 do the calculations. It's really, I would say, a nonsense here. So I prefer to use my joker. Sorry.
Okay. The opt-out card. Right. I think the other questions are also not part of your remit. So I'll hand it to Sven Olaf.
Yeah, thanks a lot for the very good presentation. As a system thinker using the, let's say, SE toolbox, we are talking also about stakeholders, and as you mentioned, that you can calculate, you can convince, you can make a forecast and so on. And a lot of people trust in this, and we can show it. But I think from the systems engineering perspective, I'm referring more to a professor from Hamburg. He's also physics and dealing with the sustainability. I'm coming more to the stakeholder, let's say, like economics or countries we mentioned. And I think we need more dramatic change in these thinking. So my question is more related maybe to a personal opinion of you. Because I think looking to our current behavior, how we grow our culture and our life, I think we need a dramatic change also in the behavior working together. So the question is, the thesis from this professor is, should we establish a new economic community and world community trading more on these prioritized activities instead of trying to change the existing trading and economic situation to really overcome and to be active, because currently we are only convincing people and running behind and saying, yes, we have to do. So the question from my point of view is maybe more view that you as the physicists and we as the system thinkers, do you see an opportunity or way that we can maybe promote these, let's say, out of the box thinking to also approach stakeholders for this transition more radical? And do you think that we both, our communities, let's say, have this chance to convince and to establish maybe a new world trading environment focusing on these rules and roles, including all countries? I'm not talking about the European countries. I'm also talking about, let's say, countries from Africa who are interested in these more sustainable thinking processes. What is your opinion?
Yeah, unfortunately, we have lost 30, 40 years by not acting quickly enough. So now we're facing the wall, we're facing the urgency. If we had started action, serious climate action like 30 years ago, it would have been much easier. Now today is unfortunately the time where solutions have to be quite radical, and we need to rethink the whole system. Now, as a polar climate scientist, I'm I couldn't give any good advice on how to do that. That's really the part of economists, system thinkers, as you are, to develop these solutions. I can only tell you what the aim would be if what we would have to do in terms of CO2 emissions reductions and other greenhouse gas emissions reductions if we want to attain a target, which would be 1 degree, 1.5 degrees or 2 degrees. But definitely, because of the time we have lost, it's really now time for urgent and radical solutions. But there's no single one solution. It actually really concerns every system at every scale, from the individual to the international collaboration. That's the unfortunate situation we are in, because we have lost so much time.
Hello, thank you very much for your speech. I have one question related to the previous one about behaviors. So we know all the evidence, no one has done anything. And we know that behaviors change when we are facing, when humans are facing consequences. To you, is there a scale of organization of, so like cities or small regions, where we could measure very short-term things and show it to people like we are progressing together as a city on something? And, or if it's not a city, is there a scale where we could measure something meaningful that we show back to people so that they can all see and get positive rewards and feedback on it?
You said the word cities. Actually, many actions have been implemented in different cities of the world by, allowing more public transport, reducing the emissions, allowing people to have lower carbon footprints, doing the adaptation measures like greening, or having more water availability. These are measures that are really often implemented in cities, much more than at the local at the smaller or agricultural scale, much more than at the national scale. It's in the cities that the real good examples can be found. Now, not every city of the world, of course, but there are some. And yeah, that's the word you have been mentioning. So there are a few examples. It's almost never enough, but a few of them exist already. Thank you.
Bo Oppenheim, Loyola Marymount University, Los Angeles. Thank you so much for this fantastic presentation. I have to admit that you put a lot of fear into me, and it has occurred to me that maybe it's time to change the name of our organization from International Council on Systems Engineering to Systems Thinking, because clearly the challenges are social, philosophical, humanistic, political. We have this tendency to dive into what's comfortable, and that's model-based. I think this is useless. Model-based is our comfort zone because we operate in the defense and aerospace industry. The real challenges are what you presented. So just pose a question that maybe we need to really rethink who we are and what we need to do. Thank you so much.
Thank you. Just one quick reply. I don't want to instill fear on people. That's not my task. I would really like you to take away the message that, yeah, we have lost time, but we still have time to limit climate change. And if we go to 1.5 or 2 degrees, that's not the end of the world. It's going to get more expensive, but it's not going to be the end of the world. So there's no reason to be fearful, but there's reason to act quickly. Thank you.
Okay, it seems that I have the last question, so I'll make it short. I heard that there is also not only a problem of burning methane natural gas, but also losing it.
Yep.
Do you have numbers? What's the rate between them? How many are we really using, and what can we win by not losing?
Yep. So that is actually, there's a huge part of today's methane emissions is actually from leakages in pipelines. Specifically in countries like, I think the worst one is Turkmenistan. So in terms of total methane emissions, it's between 5 and 10%. I'm not 100% certain about that number. I would have to check it again. It's not all of it. It's not the majority, but it's substantial. right? So the percentage of CO2 of methane emissions that we stupidly lose by leakages in pipelines and leakages in the infrastructures. That would be a part of reducing emissions that would be immediately profitable for those who sell the methane. It's better to sell it than to let it leak into the air, and it's always better to burn it than to emit it as methane, because methane is much more powerful greenhouse gas than CO2. Of course, the best would be to leave it in the ground. But yeah, it's a few percent. It's not negligible at all. I don't know the exact number. I would have to look it up. It's between 5 and 10%, I think. Thank you.
Okay, thanks a lot. Unfortunately, that's all we have time for. I've learned my lesson. I'm not allowed to be in front of the speakers. Thank you very much, Gerhard, for this really insightful and very, very interesting first keynote of the event.